Hello, I am Dipak Parmar. Today we will discuss about properties of moist air. As you know that properties of moist air are called psychrometric properties. In today's session we will discuss about following psychrometric properties: specific humidity, dew point temperature, degree of saturation, relative humidity, and enthalpy of moist air. One by one we will discuss all properties one by one. We start first property, that is called specific humidity, that is also called a humidity ratio. It is denoted by omega, and that is nothing but mass of water vapor present into air divided by mass of dry air. So it is a ratio of mass of water vapor to mass of dry air. As we know that characteristic gas equation PV equal to MRT, we can write PV equal to MRT for air, and we can write PV equal to MRT for water vapor. From that we can get a mass of air, mass of water vapor, and we can represent this mass of air and mass of water vapor ratio in terms of pressure and molecular mass of vapor and molecular mass of air, and that will come to 0.622 PV by PA. That is a 0.622 into partial pressure of water vapor divided by partial pressure of air. When we take mass of water vapor equal to 18.016 and mass of air equal to 28.966. As we know that actual pressure of atmosphere P is a summation of partial pressure of air plus summation of partial pressure of water vapor. The same equation we can represent now in terms of partial pressure of water. Now PA will be equal to P minus PV. So we can say that the specific humidity omega is a function of partial pressure of water vapor. The next topic we will discuss is dew point temperature. This is a TS diagram, and point 1 is represented over here according to its dry bulb temperature. This point is in a vapor zone, so we can call it is a superheated state of water vapor in unsaturated air, and its partial pressure is this. Now if we can keep partial pressure of water vapor constant and by some means we cool it, the step by step the point the temperature will decrease, and there will be a point after some time when it will reach to a saturation condition, and when it will reach to a saturation condition, the first dew from water vapor will be formed, and that temperature is called a dew point temperature. So in short, dew point temperature is a temperature at which the first dew of water vapor will be formed when cooling it by keeping partial pressure of water vapor constant. So this temperature is dry bulb temperature. This temperature is dew point temperature. Third property we will discuss is degree of saturation. That also we will understand by TS diagram. I have a point 1 that is again a superheated water vapor in unsaturated air. I have another point that is point 2, that is a saturated water vapor in a saturated air. Initially I have a point 1 whose partial pressure is PV. Second point which I have shown is a saturated water vapor in saturated air, that is point 2, and its pressure is PS. We can see here that if I have one state, by some means if I go on adding the water vapor into air by keeping its temperature constant, the step by step its partial pressure will increase, and After this process, multiple process, the vapor will be converted into a water will be converted into a vapor, and it will follow this line, and there will be a point where the capacity of air absorbing water vapor will stop, and that point we can call is a saturation point. This will be a saturation condition at this temperature. Once you have this point, point 1, you can get the specific humidity of point 1. After vaporization, when it comes to point 2, we can calculate specific humidity at point 2. And if you take the ratio of specific humidity at point 1 divided by specific humidity at point 2, that is nothing but a saturation condition. This ratio is called degree of saturation. In terms of pressure, it can be written like this. Third term we have is a relative humidity. The relative humidity is a ratio of mass of water vapor divided by mass of water vapor in a saturated condition of a given volume and given temperature. That we will understand by this. Suppose we have a one person who can eat 5 chapatis. So 5 chapati eating is his capacity. But suppose he has taken only 2 chapatis, then the ratio will come 2 by 5. 5 is a saturation condition, 2 is actual condition. Same way in case of moist air, the ratio represents the mass of water vapor present, that is actual condition, and mass of water vapor present in a saturation condition, that is a capacity. So actual condition by capacity we represent the relative humidity. In terms of pressure, we can represent relative humidity by PV by PS. Same way in terms of volume, we can represent by Vs by Vv. These are the some correlations which will show the correlation in between specific humidity, relative humidity, and degree of saturation in terms of partial pressure of air, saturation pressure, and total pressure. Next is enthalpy of moist air. As we know that when we talk about moist air, it is having dry air plus some water vapor present into there. So according to Gibbs law, if we want to calculate an enthalpy of moist air, it will be a summation of enthalpy of dry air plus specific humidity into enthalpy of water vapor. Let us understand one by one. Again, we are having a TS diagram where A point is an actual moist air. If I want to calculate enthalpy at point A, then it will be an enthalpy of dry air at A. So that will be a Cp into T. The temperature of A is T. Now plus summation of enthalpy of water vapor. This point, if my vapor will be in unsaturated, superheated water vapor in unsaturated air. So if I want to get the enthalpy at point A, it will be an enthalpy of sensible heat, enthalpy of latent heat, and enthalpy, that is called heat of superheat. So summation of sensible heat, latent heat, and heat of superheat will give me the enthalpy of vapor. You multiply this value with the omega, that is a specific humidity, and summation of enthalpy of dry air plus enthalpy of water vapor into omega specific humidity will give the enthalpy of moist air, where HA is Cp into T, where Cp is specific heat of air, that is 1.005 kilojoule per kg Kelvin. When we calculate enthalpy of water vapor, it will be a Cp of water into Td plus HFC, that is latent heat, plus Cp of water vapor into delta T, that is superheat temperature. We will take the Cp of water equal to 4.186 kilojoule per kg Kelvin, and specific heat of vapor is 1.88. Now we will discuss about weight bulb temperature. You must have seen a thermometer like where in which one thermometer will give you the dry bulb temperature and second thermometer, of which the bulb is surrounded by wet cloth, and this temperature it will show is wet bulb temperature. To calculate wet bulb temperature, we are having an apparatus that is called sling psychrometer, in which we are having a one thermometer, second thermometer, and then second thermometer is covered with a wet cloth, and we are have a handlebar. By rotating this sling psychrometer will rotate. When it will rotate, the air will pass through this cloth, a wet cloth. When air will pass through this wet cloth, the cooling will happen in the water present into a cloth, and the temperature which we measure, that is a temperature of this water particle present into a wet cloth, and that temperature is called wet bulb temperature. Let us understand this phenomena. Again, we are having a TS diagram in which I have a point A. So A is a superheated state of water vapor in unsaturated air, and its partial pressure is PV. At the same temperature, the saturation pressure is PS, and there is a vast difference between saturation pressure and partial pressure of water vapor. As this partial pressure of water vapor is less than the saturation pressure at that temperature, there is a tendency of water which will be converted into a vapor when air is passing over here. So when the thermometer is surrounded by a wet cloth, the partial pressure of that is high, quite high at that given temperature compared to the partial pressure of water vapor present into air. So what will happen when air is passing through a wet cloth? The water particle present into a wet cloth will try to evaporate, as there is a pressure difference of saturation and partial. So some water particle will evaporate. As some water particle will evaporate, for evaporation purpose, the water particles require heat. That heat the water particles will take from air as well as water. So when evaporated water will take heat from water itself, and when they will be converted into a vapor, there will be an increment in partial pressure of water vapor, and there will be decrement in the temperature of water particle present onto a wet cloth. So it will be shifted, the water temperature will be shifted to this point, and partial pressure of now air by after addition of the vapor will be shifted to PV1 here. This process, again, this pressure, new partial pressure of vapor is still less than the saturation condition at this point. So this process will continue till your partial pressure of water vapor and saturation pressure becomes equal. So this process will continue. Again, the water temperature will decrease. The point will be shifted to this, and this process will continue till the partial pressure of water vapor and saturation pressure becomes equal. So this is the point. After getting evaporation, the point will come where the partial pressure of water vapor and saturation pressure becomes equal. Now this process, evaporation process, will stop, and at that time, whatever is the temperature of that wet cloth, water particle in a wet cloth, that temperature is called wet bulb temperature. So this is initial temperature, that is a dry bulb temperature. After passing through number of cycles, it will reach to a point where saturation pressure and partial pressure will become equal. This point temperature is called a wet bulb temperature. So this is a wet bulb temperature. Thank you very much.